recording started sooner than I thought. So we have Clélia Pech, who has kindly written her title, Motivic integration for some varieties with a torus action.
All right, thanks very much. It's really nice to be able to talk here. So first I'd like to tell you a little bit about the setting. So I'm going to consider some varieties that have torus action but are not toric. So these will be T varieties of complexity 1, which means that the minimal codimension of an orbit is 1 and not 0, like it would be for toric varieties. So X is a normal T variety of complexity 1. And the complexity, this is the minimum codimension of the T orbit. And so the idea is that we'd like to compute some invariants called, stringy invariants, which were introduced by Batyrev. For these varieties. So what I'd like to, so just remark is that complexity 0, that's just a toric variety. And what I'm going to talk about, that has been studied by Ishii in 2004. Also, in theory, our papers is more general than just T varieties, but the combinatorics gets really messy, so I decided to focus on torus actions here. So the results work for horospherical G varieties of complexity 1. So these are some particular G varieties. Complexity means the same thing except for G orbit. I'm not going to go there because there's really a lot of combinatorics involved. And also, in the case of complexity 0, so G varieties of complexity 0, horospherical, I should say. This has been dealt with by Batyrev and Raibaut. Okay, so some motivation for what I'll be explaining is that, we want to compute Batyrev's stringy invariants. So I'll explain the definition a little bit later. So they give us an equivalent of Hodge numbers for singular varieties. And so Batyrev introduced them to be able to state some mirror symmetry conjectures for KAH varieties that were singular. So, with potential, so we haven't done it, but there are potential applications to mirror symmetry. And so one of the consequences of our results is that we can get a smoothness criterion for these varieties. It has some restrictions, but I'll explain that in due course. Right, so that was for the introduction, and now what I like to do is define these stringy invariants. Is that okay? Can you see the top, or should I lower it? So the setup is one of those T varieties of complexity 1, but I'm going to make some further assumptions. So first, I'm going to start with Q Gorenstein variety. So I'm going to ask that that any canonical divisor is Q Cartier. So for here, I don't need T variety. So I'm just going to say that X is normal Q Gorenstein. I should have said earlier that I'm always over C. And so I'm going to consider resolutions of singularities for such varieties, and so here the resolution of singularities. So my X prime here is smooth, and I also have that, well, this is a birational proper morphism, and I want the exceptional locus to be finitely many normal crossings divisors. So, okay, so I should say F proper and birational, and the exceptional locus so E is the union of some EIs. This is a finite set. And now this thing, and so these are smooth and non-crossings divided. Okay, and with that setup, I can now define so I can now define what's called the stringy Motivic volume. So, but first, let me write. So I define the relative canonical divisor to be so it will have components on. So it will be a formal sum of these EIs, and so sum over I of some UI. EI, these are, and I will require so. UI to be bigger than -1, so this is asking for a log terminal. And so now the formula, so then I can introduce this. So it will be, so a priori not a polynomial. So what I do is that I take a sum over all the subsets I. So, and then I look at the class of, well, this I will explain what that is. Right, I'll just write it and then I'll say what everything is. So, this one over plus 1, so that's why we need this assumption here. And, right, so here, so this EJ0 it's defined as taking, so I take the intersection of all the components in that set, so intersection J, capital J of E J, and I remove from this the union of the things that are not in the set J. Right, so that the L here, this is the class of A1, and everything here lives in what I will call the, well, so it's in some completion and localization of the Grothendieck ring of algebraic varieties. So this leaves. So I will write that M hat C of L to the 1 over M. So this, so M at C is completion this. So completion that is made to ensure that the L to the minus n tends to 0. And here, so the 1 over m, this little m, is the GCD of all the denominators of these new I. And oh, and the name of that thing, this is called the stringy Motivic volume of X.
Okay, I have a question.
Yeah.
I have this memory of there being a result that the affine line is a zero divisor.
Yeah.
So are you inverting it?
Well, you can, yeah, it is true that it is a zero divisor, but it is not, it's a zero divisor, but it's not nilpotent. Wait, yeah, I think that's,
I see.
yeah, so you can make sense of this, but it is, yeah, that's true, there's a result like that.
Okay.
Yeah, I haven't quite. It's true. Yeah, I'm not really explaining much about the construction there, but it is. Yeah, it is fine. Yeah. So now, well, this is a definition. What I'd like to say is that this is actually a nice thing when if you have a smooth variety, it recovers something familiar. And then I'd like to say how you can compute this thing using Motivic integration on the arc space of the variety X.
Does it make sense to say that it doesn't depend on the resolution?
Yes, it doesn't depend on the resolution. Yeah, it's not clear, but it will be clear when I mean clearer. Yeah, I think it will be much clearer when I write it in terms of Motivic integration. Then that's. But yeah, it is not obvious a priori why this doesn't depend on the resolution, but it does. So,
So here your gamma I is rational number, not integer.
yeah, these are rational numbers. Yeah, so I've said that this is, so yeah, exactly, that's why I have to do this, this here, because a priori, the denominators of these could, so L to powers 1 over some denominators of new j's could appear, so that's why I'm doing this.
Maybe I'm not so familiar. When
Yeah.
x is a smooth, for example.
Yeah,
then
yeah.
What is this exactly?
Yeah, I'm going to do that. Yeah, because I think it's useful. Yeah. So this will recover So okay, let me. So associated to this definition, there is the stringy e function, which is almost the same, except we make it a function. So we replace L by uv of where u. So this is just, what notation is it? So now we are introducing two variables, and this is very similar. So this would be the usual, so this is the usual Hodge Grothendieck polynomial, and here we're taking that term, replacing it's like replacing L with the product U times E. And okay, so that's like the Hodge polynomial. So this is, I haven't put the 0 here, so what I do almost the same as here, except I don't remove this. And now this, so if the variety is smooth, that gives you the, so if x was already smooth, that would give you the original e function. So
Now here why you need x normal? This polynomial works for any x.
This polynomial well, this, I mean, I should say this is not necessarily a polynomial if x is not smooth.
No, it is. I mean this. I mean this virtual Hodge polynomial exists for any x. I think your construction here is similar to the virtual.
Okay.
Virtual Hodge polynomial.
That could be that. I mean that I don't know. Yeah.
I think they are the same.
So I would need to check in Batyrev's paper because that's where I've taken the definition from. So I think he might be. I don't want to get it wrong. He might be making these assumptions there, but it could be that they're not necessary.
So I think here there's only you want to get various notion of singularity for x, right?
Yeah.
So what?
But here I also need it. I also need it.
No, you can use this one. You can use others, but the computation here is no matter how complex it is. I mean, but the thing on net, this the thing.
This stringy.
Yeah, and the Hodge number, Hodge polynomial. virtual Hodge polynomial for any variety. That's unique.
Okay. Okay. So so that's something I don't know about. Then I guess it would coincide. Yeah, this definition would coincide with what you're saying.
I think it must be the same. Otherwise, I mean, I cannot understand if they're different.
No, I think it should be, because the way I understand these things are defined is that it kind of ensures that it's, if they define the same thing for smooth variety, then they should also.
And this works for any x, not only for normal one.
Okay, no, I believe you. But I've seen the way I've taken it from Batyrev's paper, and I thought he was making this assumption here. But then, okay, that's good to know. Right. So we can also then evaluate, well, kind of evaluate this at uv equals 1, and that would give us the stringy Euler characteristic. So then it's possible as well, as you say, that it's defined more generally, but in my context, then I can compute it in that way. So this, that will be, so I take the sum again of over all the subset of I, the Euler characteristic of this, and then I get the 1 over, so if I kind of formally replace u and b by 1, this gives me a product of 1 uj plus 1. Okay. And now I'd like to explain how this can be computed by integrating over the arc space of x prime. So, yeah, let's. So, I'm just going to recall the definition if, because I'm usually I don't come from this area, I'm more of a horospherical person. So for me, this would be necessary, but if you're bored and you want me to not give all those definitions, just stop me. So I'm going to call Lm of x the mjet scheme of x. And it is, so its points are morphisms from set of C of T multi-n plus 1 to my variety x.
So I also don't know why it is called a string something. This is just Euler. Right?
That's not me, that's Batyrev. So that's how it's called in the paper. I
think this number coincides with the Euler-Euler number. But in this way, I think it's more subtle. We don't know if this is an integer, right? So
no, this is not an integer in general. So I'll do an example at the end. It's a rational number. It will be 6 over 5. This doesn't have to be an integer.
But this made me more confusing. So the Euler number, this is from the virtual Hodge number, something from virtual Hodge number is coincide with the Euler number defined use topology. Use cohomology. I mean the Euler number. So I think this one, this is one of the example of additive invariants.
Yeah,
This
these
was
are
getting- was
additive
getting
invariants. Yeah.
In Noether and I don't know how to spell it. Noether.
Loser.
And then,
Oh, yeah.
In 2005, something.
Yeah,
right.
yeah. That comes from.
This is one of the examples.
Yeah.
On that, you can choose the end use as you want, right?
Um,
As long as it's bigger than.
yeah, but this
Obviously cannot
change
be-
depending on the resolution, but this will also change.
Yeah.
So it's not obvious why they would be. I agree, it's not obvious now why it doesn't depend on the resolution. It's not obvious at all. But it's proved in this paper of Batyrev that it doesn't. And I think the expression as in terms of Motivic integration makes it a little bit clearer, because there, at least it only kind of depends. Well, I don't know if it's much clearer, but it will depend on the order of the anticanonical, the relative anticanonical divisor over the arc space. So I don't, yeah. Well, we'll see, and maybe that is clearer, or maybe it's not. But okay. So yeah, so that's the jet scheme, and then we can define this as the projective limit. And I'm going to introduce for later use some morphism, so the points are morphisms from spec of C of P. I'm sorry, not this. Double thing. So that's, I may call O later, sometimes, to X. And by, so I have some truncation morphisms like this, which I will use later. And so what we want is we want to be able to associate to some subsets of this, some particular subsets. We want to associate some element in that ring here. So what is a cylinder? So the typical measurable subsets here are cylinders, and then all the other measurable systems are approximations of cylinders. But I will only stick to explaining what the cylinders are. So if I have C inside L of X, I call it a cylinder. If there exists some integer m0 such that when I take the image by pi m0, so when I truncate, then I get a constructible set inside the jet space, and I also want C to coincide. So okay, so pi m0 of C is constructible, and I want C to be the same as pi m0 inverse pi m0 of C. So that will be the typical measurable set. So And then I can associate to that its Motivic measure. So to define it, I take the class of pi m of C where this is any integer larger than the m0 for which I get a constructible set. And then I do L to the minus md, where d is the dimension of x. And this doesn't depend on the choice of m larger than m0, because you also have some morphisms between different jet spaces, and there's some compatibility. So this doesn't depend on m larger than m0. And then, so this is a cylinder, and measurable subsets are very closely related to cylinders, a sort of approximation of cylinders. So now that I have this, I can define what it is to be a measurable function. So if I have a function f, which goes, so it takes integer values, possibly including infinity. So we'll see that a typical example, like this, the prototype of such functions are going to be order along subschemes. So such a function is measurable if when I take the pre-image of any of these, I get a measurable subspace of the arc space. So for n in S, so that means that this is more or less a cylinder, and now so that's measurable. And now if I want to integrate it, I need more. So I need the pre-image of infinity to have measure 0, and also I want some series to converge, and then I will be integrable. So if, moreover, the measure of this is 0, because otherwise you'll run into trouble when trying to sum, and the series, which I'm going to write down in here, so the sum so I'm going to integrate over some cylinder. So I need, so what's relevant is the measure of the intersection. So that's where I'm going to integrate on. So the relevant data is the measure of this, and then L to the minus S, if this converges, then I say that F is integrable. Well, on C, and the formula for the integral, so the integral over C, so this is just notation, but I write this as L to the minus F d mu x. So this is, that's the notation I had used for here. So this I define is also I do some of that for you. Right, and that yeah, that's the definition of the integral. And now these stringy invariants can be computed by integrating here with f being the order along the relative canonical divisor of the resolution. Yeah.
The fiber over infinity doesn't intervene at any point.
Doesn't need to.
I mean, what is the point of allowing infinity as a value?
Well, it can, with the examples of order along something, it could technically, I think it could technically happen. Yeah, I mean, I guess maybe if you take, yeah, it seems difficult to have.
I mean, it's
I'm
okay,
trying to
it's just
think
that
in
it
the
doesn't
typical-
come up in the reminder.
In the typical example. Yeah. Yeah, I see what you mean. I don't have on the top of my head the reason why. I'm sure. I saw this. I think it's probably Denef and Lozer, where I've taken definitions from. So I'm assuming there must be situations where you need it, but I don't know. Yeah.
What's the meaning of convergence?
Mu of
Convergence. Convergence in all the things.
this.
Yes.
Okay. Well, this would be in the Motivic ring, the completed Motivic ring, and you can define the notion of limit there. So this lives in this MC hat. And in this, for instance, you can make sense of the limit of L to the minus n being 0 as n tends to infinity. So this, you can make sense of the notion of convergence of these things there. It wouldn't make sense if you didn't complete, but
Combination of a ring.
yeah, yeah. This is, so I erased it, but this is. And when I take the class, so, and the L is the class of the affine line. Sorry, it's a completion of this.
Okay.
So-
So can you remind me? So sequence tends to 0 was mean.
So this is the completion is so that this tends to 0.
Only L minus infinity to 0. This is.
Yeah. Yeah. And so, okay, so now, write the theorem that is, so in Batyrev's paper, then says so that you can compute this stringy Motivic volume as integral over the arc space of the resolution. So I put myself in the same situation as before with the resolution of the singularities of X, and with L to the minus order along this d mu X prime. And if X is smooth, then this is just gives you the class of X. So that's what we'd like to do now for these T varieties. We'd like to use this. But before, okay, so now I'd like to explain how we can work with T varieties of complexity 1. So the model for the combinatorics I introduced here, this is the combinatorics around toric varieties, so fans. And this is true in any complexity, and for G varieties, you have a combinatorial description that you can find in Timashev's book, for instance, but it is kind of much simpler. So if X is T variety of complexity 1, then what's really nice is that X is T equivariantly birationally equivalent to a product of C times the torus, where and C is just a curve. So C is a smooth projective curve. So this is not, it's just birational, but T equivariantly birational to a product of a curve and the torus. So the first part of the data that I'm going to associate to such a variety will be the curve and the torus. But then this only describes the birational model, so I want to be more precise, and that's where I'll introduce some equivalent of the fan. So I will set M to be characters, the torus, and the dual. And if we were in the toric setting, then I would define some cones and a fan. And what I'm going to do is not very different. So I will consider some sigma inside, well, the Q vector space corresponding with N, and strongly polyhedral strongly convex polyhedral cone. So that means that 0 is a phase. And I will consider also C0 smooth curve. So for later use, C0 will be a subset of the C here. And to that data, so corresponding to that data, I can define some formal sum of, so a sigma polyhedral divisor not really a divisor. We'll need to evaluate it on points here to make it really a divisor. But that's the name. So this, the reference for this is Altman 1000. So it is a formal sum. So D, I will write it as a sum over points in the curve C0 of something times the point. So if I had rational numbers here, that would be a divisor, but that's not what I choose. I put some delta y, and the delta y would be a Minkowski, the Minkowski sum of some convex hull of finitely many points and the cone sigma. So delta y is, so it's some sort of so it's some part of NQ. So many points in NQ and sigma. So they all contain, all of these contain sigma. So my original cone, and I also require that actually almost always this will be sigma. So such that delta y is just sigma, except for finitely many points. So now, associated with that, I can define so I will define an affine T variety associated with the data of such a D and C0. And then if I want to do something non-affine, then I will need to consider a fan of those objects with some compatibility conditions, just like you would for toric variety. I mean, it's a little bit different, but it's the same idea. So now, to define the affine variety, I introduce this algebra A C0 of D, and this is so now I take an element M which is in the dual of the cone sigma, but it's a lattice point, and then global sections here. So this lives, this subalgebra lives inside the functions on C0. And this, so this chi of M, I just if I have an element M on the lattice, I define the corresponding element here as K of M. So, okay, D of M, what is it? I said this is kind of not a divisor, but I can make it a divisor. So by evaluating on the point M of the lattice. So this is a bit. So this is based on evaluating points here against a point in M. So this lives in NQ. So this is just so a priori that would be rational numbers, but I just want the integral part, right? And now x of C0D, this will be spectrum of this. And this is a prototype of an affine T-variety of complexity 1. So if you have an affine T-variety of complexity 1, then you can always choose a polyhedral divisor and a curve such that the variety is like this. And now if in the non-affine case, you need fans. So right, and now briefly in the time I still have, so I'd like to explain how we can use some of that combinatorial data to understand the arc space. So in the toric case, so I mentioned at the beginning that the computation of the stringy invariant has been done by Ishii in the toric case. And what she did is that she looked at the T of O orbits in the arc space. So O being O is this. Right. So she looked at the T of O orbits. They are countable, and on each of those orbits, you have a very nice combinatorial description for the order along the relative anticanonical divisor. And she just summed over this to get the stringy volume. Right. In our case, we could do the same. So we would be using the same idea. So we can look at the arc space and use all our combinatorial data to try and understand this order function. But there is a problem, is that we no longer have countably many T of O orbits. So the idea for computing this is that, so in the toric case, we decompose the arc space into T of O orbits. And so on which this function is easy to compute. And so on. But we have too many orbits in our case, so in complexity 1, so there are uncountably many orbits. So what we do is that we cut the arc space in two parts. There's one where we can ensure that we have countably many orbits, and the rest happens to have Motivic measure 0, so will not contribute. So we divide. In two parts. One which we called vertical arcs, and these have measure 0. And we have horizontal arcs where we have finitely many T orbits. Not finitely, countably, sorry. Well, and it's a bit painful, but the combinatorial data I've given here also enable us to understand this function and to compute the integral. So I'd like to finish. So we have a formula for the stringy Motivic volume, but to explain it, I will need to say more about the combinatorics. So instead, I'll just say something about the stringy Euler characteristics. So what we can prove is that, so if T is a sigma probability divisor, with affine C0, so the curve over which I've defined this divisor. And I also need this to be local factorial. Then we can always check that this stringy Euler characteristic is bigger than the usual Euler characteristic. So if this data, if the Euler characteristic of C0 is not 0, then equality holds if and only if X is smooth. So this is a bit annoying, this condition, but it happens because if we use, our formula for computing this, and then if you compute this, this appears on both sides, so there's really no way to avoid it as far as we've seen. Okay, so yeah, that's all I wanted to say. Yeah, I didn't have time to give an example, but there are some very concrete hypersurfaces where you can compute all of this, and there's one where that has Euler characteristic 1, but where here you can compute it using these techniques, and you get 6/5, and then it's not smooth.
Questions?
So for instance, C0 cannot be an elliptic curve.
Yeah, I mean, I already required it here to be affine. Yeah. Yeah, I mean, no, well, what I need is 2 minus twice the genus of some curve C minus
Then remove
C minus C0 different from 0. But yeah, this is. So C is the smooth projective curve giving us the birational type. So this C there could a priori be elliptic, but then we will need something on C0 to make sure that this number is not 0. This C0 is the locus on which we define the divisor. It's not necessarily the one that gives us the birational type of the variety.
I'm still not very clear on how much this choice of new eyes
Yeah.
is important. Because in your conclusion, like the Euler characteristic of X does not depend on
Yeah.
the choices, but the thing on the left
It doesn't.
should depend.
No, it doesn't. This is. I'm really sorry that I haven't looked recently at Batyrev's paper, and I cannot remember why this is true, but this is true that it doesn't depend. Maybe I can look at it and I'll try to tell you, because I agree. I thought that we would get to a stage where that was clear, but none of the formulas I gave make it clear.
So here, I'm not quite understand what is your instruction in this field. So XD, this means a rhetoric variety. No, XD, X.
T, yeah, T.
X.
Yeah, X. Or X of D is not toric, no. It is a T variety, but it has. Well, I mean, it depends. For me, toric, I understand that you have an open orbit isomorphic to T, and I don't have that. So this has complexity 1.
So that means
like
birational to a curve times a rhetoric variety.
yeah.
So D is a divisor of X. Yes.
It's not really a divisor. You need to.
So corresponding to a divisor of X. Oh.
Sorry?
So determine a divisor.
Yeah, it determines actually loads of them once you evaluate it over any element of the lattice M, which is the character lattice of T.
So now C0 geometrically what's it?
So this is, so in the definition of D, I sum over points on a curve C0. This is inside. It's a curve that's inside C, but I'm not forcing D to be defined over the same locus as this projective C. So here in particular, C will always be projective, and here I require affine C0. So it occurs here. The way C0 appears is in the definition of the ring here.
So what I'm confusing is, so your E string is an additive invariant or not?
Yeah, it is.
is an
additive, yeah.
additive. But if this additive invariant, I think that it should be equal to EX. So it should be unique. If this in smooth case that's the same, then it must be the same for the singular case. So here you see the smooth case that's equal, right? Then since this additive, so the singular case it should be also equal. So
It sounds like you two have something to talk about this afternoon. All right, let's thanks.